we looked at derivation of conservation of mass, momentum and energy, right. Today we are going to see if we can solve the fluid flow and heat transfer using these equations with the required number of unknowns that we have, okay. So we have looked at conservation of mass, momentum and energy, right. So essentially how many equations we have? We have one equation for mass, right, and momentum equation is how many? 3 of them, right. We have one in each direction, and then energy equation is one equation. So essentially we have 5 equations at our disposal, okay. And how many unknowns we have? So how many unknowns do we have? We have what are the unknowns we have? For a compressible fluid, right, general compressible fluid that we have derived U, right. So essentially U, you mean U bar, right, essentially U V W, so that is 3 unknowns, right. And then we have pressure is an unknown, right, pressure is an unknown, and then density rho is an unknown. Then we have an equation for internal energy E, right. So little e is an unknown, and then temperature T is also an unknown, right. Unless we have a special relation which relates internal energy to the density, we do not know the relation between these two, right. So as a result, E is an unknown and T is an unknown. So how many unknowns do we have in total? We have 3 plus 4, right. We have a total of 7 unknowns, whereas the number of equations we have are only 5, right. So can we solve for this 7 unknowns with these equations? We cannot of course solve for this. So we need to invoke further assumptions, right. So we need to invoke something known as thermodynamic equilibrium. We need to invoke something known as thermodynamic equilibrium, right. What does the thermodynamic equilibrium mean? It means that if you have a simple compressible system, right, assuming that that is in thermodynamic equilibrium, then we just need 2 independent intensive properties to completely specify the state of the system, okay. So essentially the state principle, what we have is we need 2 independent intensive properties to completely specify the state of the system, right, if we have a simple compressible system, right. That means there are no other external forces acting on it on this particular system, okay. So we just need 2 independent intensive properties, and all other properties can be obtained from these independent properties that we have specified, okay. So if we choose as our properties as let us say density and temperature as our independent properties, okay, then what we can do is we can go about and write and relate the other properties. So for example, we choose let us say density and temperature as the independent properties. Then the other 2 quantities, that is the other 2 thermodynamic variables, that is pressure and internal energy. So pressure can be obtained as a function of density and temperature. Similarly, the internal energy E as a function of density and temperature, right. So essentially we have now 2 more equations, right. So this is the 6th equation, and then we have the 7th equation, right. So essentially we have 7 equations and 7 unknowns as we go here, right. So we have plus 2 here, which gives us 7 equations and 7 unknowns. So theoretically, in principle, we can solve for all the set of variables, okay. So what is the principle that gives us these 2? This is known as the equation of state, right. Essentially equation of state for a particular fluid relates the pressure and internal energy to the density and temperature variations, right. So, essentially equation of state gives us these extra equations, okay, which I would probably write it as sometimes as EOS, okay, as a short form. Now, if you have a perfect gas, then we know that the pressure is related to the density and temperature using what? Ideal gas equation, that is P equals rho RT, and the internal energy for a fluid, right, for a perfect gas is given as CV times temperature, right, so the absolute temperature. So, we have these two equations which we use to relate density and temperature to pressure and the internal energy, okay. All right, so that is good. Now, what we can see from here is that the equation of state relates the energy equation on one hand and the mass and the momentum equations on the other hand, okay. So, essentially equation of state is the kind of connecting link between these two, okay. So, why do we say that? We say that because the energy equation contains internal energy, right, E, whereas the mass and momentum contain the density, pressure, and of course, the energy equation also contains the temperature, right. So, we have these things. Now, the changes in density and the changes in pressure cause a changes in temperature, right. Now, that is only possible if you have a compressible fluid or a compressible flow, right. Only under if you have a compressible flow or a compressible fluid, you have density changes which are caused by changes in pressure as well as temperature, okay. So, essentially what we mean is that okay, so the changes in density are caused by temperature as well as pressure if you have a compressible fluid or a compressible flow, okay. Now, this is what relates the energy equation, kind of links the energy equation to the mass and momentum equations, okay. Now, if you have an incompressible flow or a fluid for which density is constant, right. So, if we have an incompressible fluid, then what happens? Then what happens is basically you do not have any density changes. As a result, your energy equation, right, the equation for temperature or internal energy gets decoupled from your mass and momentum equations, okay. So, essentially this link will not be there between mass and momentum and energy. As a result, temperature, right, the changes in temperature are not brought about because of the changes in density or in pressure, right, if you have an incompressible fluid, okay. So, that means for incompressible fluid, the temperature or the energy equation gets decoupled from the mass and momentum equations, okay. So, what is a consequence of that? The consequence of that is the energy equation can be solved as a separate passive scalar transport equation, okay. So, this can be solved separately because it is no more coupled to the mass and momentum, okay. As a result, in many incompressible fluid flow problems, we could just get away by solving only the mass and momentum equations if we have an isothermal flow. If we are solving for a non-isothermal flow, then we have to solve for temperature as well as a separate scalar, okay, with the different boundary conditions that it has, okay. So, that is kind of the takeaway message. Now, as far as the complexity of the solution procedures is concerned, if you have a compressible flow system, then you have a equal number of equations and unknowns, right. You have 7 equations, 7 unknowns, you can solve for them one by one, okay. Now, we will see that if you have an incompressible fluid or incompressible flow, your continuity equation becomes just del dot u bar equals 0, right. As a result, you do not have an equation for density, right. So, density is again now constant, and what we will see is that this will bring about another significant change, which is basically your you have 3 equations of the momentum, which is rho du dt, rho dv dt and so on, right. You have these three equations and you end up with no equation for pressure, okay. So, as a result, the equation for pressure is only again another equation for in terms of velocities, okay. So, as a result, the solution procedures for incompressible flows are quite different from the solution procedures that you have to adopt for solving for a compressible flow, okay. So, that is what we are going to see in the rest of this course when we come to the solution of fluid flow equations for incompressible flows, okay. Questions till now? Okay, so let's move on. Okay, then let's look at Navier Stokes equations for a Newtonian fluid. Now, one thing we didn't of course consider was the shear stresses, right. We talked about tau ij, but when I have listed down the unknowns, I have comfortably not listed down the tau ij's. Neither you told me that the tau ij is still an unknown, right. We all assume that tau ij's are unknown, right. That is kind of good, but we know that these are still unknown at this point of time, right. The shear stresses that we have in the momentum equations are still unknowns. Nobody told us how to evaluate these terms, right. These are still unknowns at this point of time, okay, which we kind of assumed while deriving this unknown and the equations balance that these are somehow known, okay. So, we assumed that these are known, which is what we are going to now discuss. How do we introduce or how do we model the shear stresses, okay. So, the tau ij, the 9 terms that we have, out of which the 6 are the independent ones for an isotropic fluid, are the ones which needs to be somehow kind of need a model, right, to specify them in terms of the other solution variables that we have, okay. So, we need a model to specify these in terms of solution variables, okay. Now, by introducing a model for this, we are going to derive the most useful form of momentum equations. All right. So, a commonly used model is to relate the shear stresses to to the deformation rates, okay, or the strain rates in a fluid. So, that is what we are going to use as a model which was proposed by Navier and Stokes in the 19th century, and then that is what we are going to use and kind of substitute these back into the momentum equations and derive the Navier Stokes equations, okay. So, the local deformation rate is composed of what? It's composed of linear deformations, right, shear deformations as well as volumetric deformations, right. So, the strain rate contains the linear or the angular, right, deformation rates as well as volumetric deformation rate, okay. So, this is a deformation rate, okay. So, essentially if you take a fluid element, in general you can model the change of a fluid element at a time t naught to another time t naught plus delta t by a series of elementary superpositions, right. These superpositions would be, you would recall from a fluid mechanics course, that will be composed of translation, a pure rigid body translation, a pure rigid body rotation, and fluid deformation, okay. And this fluid deformation would be again composed of two components. One is angular deformation, right, and the one is a volumetric deformation, okay. So essentially you have all these four. We are only looking at only the later part, which is the fluid deformation, okay, the angular and the volumetric deformations, because the other two do not come into picture in modeling the shear stresses that we have for a fluid, okay. All right. So we call these as the strain rates or the strain rate tensor, okay, which has again 9 components, out of which 6 are independent if we have an isotropic fluid, okay. So how do we represent these deformation rates? We have 3 components of, linear elongation strain rates. These are given as, so we use the symbol S sub ij, okay. So we have, just like we have tau ij, we use this S sub ij to represent the strain rates, okay. So again ij go from x, y, z each of them. So the linear elongation strain rates would constitute S sub xx equals 2 times partial u partial x, okay. This would be 2 times partial u partial x. Syy would be equal to 2 times partial v partial y. Szz equals 2 times partial w partial z, okay. Would there be a 2 here? No 2, right? It's just this is just partial u partial x partial v partial y partial w partial z, that is for the linear elongation strain rates. And when it comes to the 6 components of shear elongation rates, elongation strain rates, so these are the angular deformation rates. So that is S sub xy equals half of partial u partial y plus partial v partial x, okay. Now you see that how, if you have S sub xx, how do you get partial u partial x? Where you have 2 of them summing up to 1, okay. So there is no 2 in there as I wrote before. Similarly, syz would be equal to half of partial v partial z plus partial w partial y, okay. Similarly, sxz would be equal to half of partial u partial z plus partial w partial x. Okay, now this looks like we can write in a convenient summation notation a very simple formula that would be nothing but S sub ij would be equal to what? Half of, right, partial u I by partial xj plus partial u j by partial xi, right. That is all, where we plug in I equals I and j as x, y, z each of them and get these 3 components of the linear deformation rates. And of course, I said 6 components of shear elongation shear rates, right. I am sorry, I think I wrote elongation here, there is no elongation, this is just shear strain rates, right. So what about the other 3? They are the same as this, right, because of the isotropy, fine. So we have all these strain rates that we get, and of course we have this additional volumetric deformation rate, which is given by what? Which is the sum of partial u partial x, partial v partial y and partial w partial z, right. So in a convenient form we can write this as del dot u bar, right, which would be 0 for if you have an incompressible fluid or incompressible flow, which is not 0 if you have a compressible fluid, right. Okay. We are still talking about a general compressible fluid, okay. All right. Now, we have introduced this model. Now, we need to know how do we relate the shear stresses that we got, the viscous stresses, to these strain rates, right. So, if we consider Newton's law of viscosity, right, then the Newton's law of viscosity relates the viscous stresses that we have to the strain rates, and then the strain rates are, again, we have these linear or angular strain rates, and we also have the volumetric deformation rate, right. So, essentially the Newton's law of viscosity relates the viscous stresses we have to each of these strain rates, okay. As a result, we end up with two coefficients of viscosity, okay, one relating to the linear or angular strain rates, okay, that is known as the first or the dynamic coefficient of viscosity, which is denoted with the symbol mu, okay, and the other one which is known as the second coefficient of viscosity, which is usually denoted with the symbol lambda, okay. Okay, now we are assuming a Newtonian fluid. What is a Newtonian fluid? The viscous stresses are proportional to the linearly proportional to the strain rates, okay. So, essentially that is how we get these things. So, we have a Newtonian fluid, but the fluid is still compressible, right. We are still considering a compressible fluid, but a Newtonian fluid. Would that be possible? Or should a Newtonian fluid be always incompressible? Need not be, right. You can still have a compressible fluid and it could be still a Newtonian fluid, okay. So, we are still looking at a compressible flow with the fluid behaving as a Newtonian fluid, okay. So, the viscous stresses are proportional to the linear deformation rates and as well as the volumetric deformation rates, okay. Now, if this is the case, we can again list down the viscous stresses that we have as using Newton's law of viscosity as tau sub xx as mu times 2 partial u partial x, okay. So, that is the coefficient which is making the proportionality constant go away, which is making the proportionality symbol go away. You have this first coefficient of viscosity plus you have lambda times del dot u bar, okay. So, that is your shear stress, right, the normal stress we have, this is the normal viscous stress, okay. Similarly, we can write down tau yy as 2 mu partial v partial y plus lambda times del dot u bar, okay. And we also have tau zz as 2 mu partial w partial z plus lambda times del dot u bar. Of course, we have the shear components, right, that is the tau xy equals mu times partial u partial y plus partial v partial x, right, that is what we have. Similarly, tau yz equals mu partial v partial z plus partial w partial y, and of course, you can also write down what is tau xz, okay, similarly. Okay, now, of course, the volumetric deformation rate only shows up in the normal stresses, right, because that is a linear part of the deformation rate, okay. Now, not a whole lot of stuff is known about this second coefficient of viscosity, okay. So, second coefficient of viscosity is usually taken to be from experiments, usually taken to be minus 2/3 mu, okay. This is a good approximation for gases, okay, for flow of gases. Now, of course, we know that if you have an incompressible flow, what will happen to del dot u bar? This goes to 0, so it does not matter what will be the second coefficient of viscosity anyway, okay. So, partially the success of the originally proposed minus 2/3 mu is related to the observations, right, that del dot u bar was even 0 in most of the compressible flows that were there, okay. So, as a result, the proposed lambda equals minus 2/3 mu was a huge success for over a few decades, okay. Now, we kind of tend to realize that that is because of this term going to 0 even for compressible flows, okay. Nonetheless, the effect of the second coefficient of viscosity is small even in practical flows, okay. So, the effect of lambda is small, as a result it is not going to make a whole lot of change or difference in the results even if you have a compressible flow. But anyway, we are not worried about it because we are looking at simulation of incompressible fluid flows, okay. Now, can we also write down a simple expression in terms of the index notation for the shear stresses from whatever we have proposed here, right? We can write down one. What would that be? That would be tau ij equals 2 mu, okay, 2 mu Sij, very good, okay. So, essentially what we have is 2 mu Sij, because Sij is again half of partial ui partial xj plus partial uj partial xi plus, now how do I bring in this extra component in here, which is non-zero for normal, which is 0 for the shear? I use a delta function, right, that is Kronecker delta. So, that will be what? Lambda, right, times delta ij times del dot u bar, right. Can I write this? Okay, where delta ij is the Kronecker delta function, which is equals 1 if I equals a, which is 0 if I not equals a, right. So, we can write down this one. So, this is a simple formula that relates the shear stresses to the strain rates that we have, okay. All right, now we have brought in Newton's law of viscosity and related the shear stresses to the strain rates. Now, what do we have to do? We have to plug back these shear stresses into the which equations? Into the momentum equations, right, and of course into the energy equation as well, okay. So, we will plug these back into the momentum equation and see if we can get a nice equation that we can use to further integrate, okay. So, what was our x momentum equation? If you go back, our x momentum equation was rho du dt, right, equals, what was there on the right hand side? We had a pressure term, right, that was minus partial p partial x, okay. I will first write down the equation in terms of the shear stresses. So, minus partial p partial x, then we had partial x of tau sub xx, partial y, tau yx plus partial z, tau zx. Is that all? We had a source term, right? We said plus smx, which is a source for the momentum equation in the x direction. Okay, very good. Now, can we plug in these shear stresses that we have obtained here, okay, into these equations, okay, and see what happens, okay. So, how does these equations look? So, if I plug in these, you have minus partial p partial x plus partial x of how much was tau xx? This was 2 mu partial u partial x plus partial y. What was there for, oh, and then we had this extra lambda del dot u as well, isn't it? Okay, which I have missed out. So, plus lambda times del dot u bar, okay, plus partial y of, what do we had? Mu times partial u. So, this was tau yx, this would be partial u partial y plus partial v partial x plus partial z times mu times, okay, mu times tau zx. So, this would be partial w, partial x and partial u, partial z, okay, plus we have smx, okay. Okay, very good. I will write down the V momentum equation also for the sake of completeness. So, that would be rho dV dt. So, this is the Y momentum equation, okay. Rho dV dt equals minus partial P partial Y plus I will directly write in terms of the shear stresses, okay, in terms of velocity gradients. That would be what? Partial x of, this would be tau xy, right. So, this would be mu times partial u partial y plus partial v partial x, okay, plus partial y of, this would be tau yy, right, tau sub yy, this would be 2 mu partial v partial y plus lambda times del dot u bar plus a partial z mu times, this is tau zy, right, this is tau zy. So, it will be mu times partial u, sorry, this is partial v partial z plus partial w partial y, okay, plus smy, okay. I would not write down the rho dw dt, which you can complete later, okay. Very good. Now, we have obtained all these equations which are only in terms of velocities, right. On the right hand side, now we do not have this shear stress vector anymore. As a result, our unknown velocity and its gradients appear on the right hand side, which could be obtained somehow, okay, if we know the velocity field at a particular time. Now, we are going to do some kind of a rearrangement here, so that these equations look somewhat nicer and also clean, and also they look in a more nicer way for to work with incompressible fluids, okay. So, for that we are going to work kind of rearrange some of these terms. So, I would go back to the x momentum equation, okay, and what I would like to do is I am going to split this 2 mu partial u partial x term into 2 terms, okay. So, mu dou u dou x plus mu dou u dou x, okay, and then I am going to collect one of that partial u partial x term from here, and then the other term I am going to take it is this one. This is first term of this term, which is mu times dou u dou y, and then I think there is some mistake in here, is it? No. Okay. So, I would take the second term here, I have not written consistently. So, this is dou u dou z, okay. So, I would write down these 3 terms together, and I will write down the remaining terms separately, okay. So, can you help me write this equation by looking at this? So, this is basically rho du dt equals minus partial p partial x plus, so I am writing down partial x of mu dou u dou x, okay, and then partial y of mu dou u dou y and partial z of mu dou u dou z, right. Those are the three terms we are kind of writing them together. So, that means partial x of mu dou u dou x plus partial y of mu dou u dou y plus partial z of mu times dou u dou z. Is that correct? Yeah. So, we have partial x of mu dou u dou x, okay, then partial y of mu dou u dou y, and then partial z of mu dou u dou z, right. These 3 terms I have written down together. Then what do we have? We have one more term remaining here, right, which is again mu dou u dou x operated by partial x, and then we have one term here, this is partial y of dou v dou x, then partial z of this guy, right. In all these terms, I would like to interchange the order of differentiation. For example, here instead of writing partial y of mu dou v dou x, assuming that, okay, I will come to that point. So, let me first write down these things. So, what is that remains here? So, plus, what is the first term? I would write down in some brackets here, okay, curly braces, partial x of mu dou u dou x is the first term, right, plus partial y of mu dou v dou x, right, plus partial z of mu times dou w dou x, is it? Was it x? Okay, x. So that's what remains. Plus, I think we had this del dot u, which is also remaining, isn't it? This guy, right? So that guy would be what? Yeah, so that will be partial x of lambda times del dot u bar, right? That is the remaining term. Do we have any other terms left out? We have the source term, of course. So that would be what? That would be plus smx. Okay, I have written all of these into curly braces. Okay, so is this correct? This is correct. Very good. Now let's say if we have a this entire thing in the curly braces, I am going to write it as, denote it with a new source term called Sm prime x. Okay, fine. Now we will see that Sm prime x would be equal to Smx if we have an incompressible fluid. Okay, that's what we are going to look at. So let's say if we have incompressible fluid or flow, plus we have constant viscosity. Okay, so that means our mu is also constant. If we have a constant viscosity as well as incompressible fluid, that means both my what properties are constant? Density is constant as well as mu is constant. Okay, so if my mu is constant, I can interchange the order of differentiation here, right? Instead of writing partial z mu partial w wx, right, partial wx, I can write it as partial x of mu dou w dou z, right? Okay, I would do that rearrangement and then write this curly brace term as partial x of, okay, mu dou u dou x, okay, plus I would write this as mu dou v dou y, right, because the partial x is taken out, plus mu dou w dou z, right. Can I write these terms like this, right? These terms underlined in red as can be rewritten like this by just interchanging the order of differentiation, because viscosity is now constant. Okay, plus we have, of course, this extra term is also in here. So I would go back and write this guy here, which is plus I have lambda times del dot u bar, right, plus Smx is the term in the curly braces. Now we can of course simplify this little bit better. This would be dou by dou x of mu times what would be these three terms together? Del dot u, right, this is del dot u bar, which is actually 0, plus we have lambda times del dot u bar, right, plus Smx. So as we just discussed, this term would be 0, right, so as this term, right, if we have incompressible flow or fluid with constant viscosity. Okay, so these are 0, in which case your Sm prime x is what? Is the same as Smx, okay. So this is what you have to keep in mind. So we are throwing everything, all these extra strain rate terms that we don't like into this curly braces, okay. We are throwing them into the source term, but you have to keep in mind that source term would be the same as a source term that is brought about by some body forces or any other forces, but it would not be just the same. It would have these extra terms in case you have a compressible fluid or if you have a non-constant viscosity, okay. In those things, your source term is not just coming out of the body forces, okay. Very good. Now this looks good. Of course, you can again use, if you look into some textbooks, they would use this lambda equals minus 2/3 mu, in which case you have 1 mu here and minus 2/3 mu, which would give you 1/3 mu and so on, okay. That is kind of some simplification, but nonetheless that term will go to 0, okay. So can we now rewrite this in a more compact way? Now if you take a look at these three terms, can we kind of gain some insight here. So, all these three terms are operating on only one component of velocity, that is u, right, they are all operating on u, and then there are two derivative operators, right, one is operating inside, one is operating outside. Okay, of course, we are saying that we are looking at a constant viscosity fluid, so this mu can be kind of taken out or it can be left inside. Okay. Now, can we write this in a compact way? So, this if you have dou u, dou x, dou u, dou y, dou u, dou z, that is nothing but a gradient of u, right, which will give you a vector, right. So, essentially these three terms can be written as gradient of u, okay, which is a vector, and then it has to be multiplied with mu, right. Now, eventually we have to get a scalar out of this and they have to sum together. Then if I take again we have dou by dou x, dou by dou y, dou by dou z, we have another gradient, right. So, that should be another del, but that should operate as a dot product, it should operate as a divergence, right. Divergence of mu times grad u kind of aptly puts these three terms into one term, right. So, this is del dot mu grad u. Okay. Now, we have made tremendous simplifications. So, we are going to come down and then write this in a nice way, which is rho du dt equals minus partial p partial x plus del dot mu grad u, okay, plus I am writing the source term which is Smx prime, but we know that this is same as Smx because we have incompressible flow with constant viscosity. Okay. So, even if I leave out the prime sometimes, so do not get confused, it is same as Smx whatever is brought about by the body forces. Okay. So, this is for incompressible fluid with constant viscosity. Now, the equation looks much nicer, right, much more pleasing. So, we can probably work with this than with the previous gigantic expressions we had for the shear stresses. Okay. Now, if you tell me what would be an equation for rho dou v dou t, what would that be? Minus partial p partial y, right, plus del dot mu times grad v plus Sm y. Okay. Of course, you can complete the rho dw dt equation yourself. Okay. Fine. Now, so these are what? These are the Navier Stokes equations, right? Navier Stokes equations which are independently derived by these two scientists by introducing this model for the shear stresses. Okay. So, that is important. So, the distinction between momentum equations and the Navier Stokes equations is clear, right. Essentially, momentum equations have the shear stresses as the unknowns still, whereas the Navier Stokes equations do not have the shear stresses as unknowns, right. They have a model for it which works very well, and those are the Navier Stokes equations which we will use to solve for fluid flow equations in the incompressible fluid flow regime. Okay. All right. So, now of course, we still have, if you go back to the equations, we have the energy equation which also contained shear stresses, tau xx, tau yy, all these things, which we are not going to do, but rather I am going to kind of summarize the equation. So, if you look at the energy equation, which you have to solve even if you have an incompressible fluid, only that this will be solved separately, you do not have to kind of couple them. So, what was the energy equation? If you remember back, rho times d little e dt, right, what was this? This was some, I think, minus p times del dot u bar or something like that, right. Initially we had del dot p u bar, but then we subtracted off the kinetic energy term, which gave us an equation for the internal energy, rho d dt equals minus p times del dot u bar plus del dot k grad t, right, okay, plus we had some source term Se, plus we have a lot of terms, right. We have a lot of terms in terms of shear strains, right, instead of viscous stresses, right. Instead of viscous stresses, tau ij we had a lot of terms, about 9 or 10, 9 terms, and I would like to call this, all these terms as phi, okay. So, what I mean by phi is the dissipation term which contains the tau ij terms, right. We had these u times tau xx, u times tau xy and so on, right. We had several terms. Now, what you have to do is you have to plug in the tau ij viscous stresses in terms of the strain rates, right, to eventually get all these terms in terms of partial ui by partial xj and so on, okay. If you do that, what you would see is phi would read as mu times 2 times partial u partial x square partial v partial y square partial w partial z square, okay. Plus you would see partial u by partial y partial v partial x square plus partial u partial z partial w partial x square plus you would see partial v partial z plus partial w partial y square, okay, plus lambda times del dot u bar whole square, okay. So, this is something you have to derive or rather kind of check it, okay. So, check this by plugging in the viscous stresses in terms of strain rates and then club all these terms. So, this is the dissipation term which appears on the right hand side of the energy equation, okay. Now, what is the first thing you notice about the dissipation term? Of course, it is composed of the strain rates, okay, but what is the thing that is there that kind of catches your eye? Squares, viscosity, okay, we have the viscosity, we have the mu and del lambda that is there, but the terms are all squared now, right. So, what about the values we have? So, these are there. So, essentially what will this term be if we have let us say incompressible flow or a fluid, this term is anyway 0, the second term is anyway 0, right. Now, what will happen to the, so this term on phi is always a positive quantity, right, because of the square. So, this is always a positive quantity. Now, what is it actually doing? It is actually, what it is actually doing is you have the strain rates which are the deformation rates which describe the deformation of the fluid particles or fluid as it flows through, right, and you are getting the deformations, right, which is described by this phi, which is acting as a source term on the right hand side of the energy equation, right. So, this is basically dissipation because it is converting the mechanical energy which is the partial u by partial xj, right, all these terms, that is the mechanical energy, right, of the fluid into thermal energy, right. It is creating the internal energy or temperature, right, essentially it is increasing the internal energy of the system. So, the dissipation term always tries to increase the internal energy of the fluid by extracting the energy from the mechanical component of the fluid, okay. So, that is responsible for the change in internal energy by converting the mechanical energy into the thermal energy, right, okay. So, that is the only link, okay, fine. So, now we have looked at the complete set of Navier Stokes equations including the energy equation by introducing the model for the shear stresses, okay. So, what we are going to do next is we are going to list down all the equations one by one and then see if we can kind of come up with a common equation that can represent all these equations, right. If you see, there are several of these terms are common between all these equations, right. You have an unsteady term, you have a convection term and then you have a divergence term and so on, right. So, we are going to kind of list down all these equations one by one and then see if we can find some commonalities between them and then thereafter go from there, okay. So, okay, thank you.